Greetings, calculus fans. In this video, we're going to be talking about Taylor-Maclaurin series. So these series are how we generally find power series for other functions. So I'll give you some motivation. We'll talk about how we know these series converge, and then we'll kind of provide you a summary in which we talk about some basic power series for other functions and an example of how to use those power series. Okay, so suppose that we have some power series represented by this sort of general expansion. So f of x is the sum n equals 0 to infinity, c sub n x minus a to the n power, and we know that this is a power series for some function x f on some radius of convergence. So what we want to try to figure out here is how the coefficients Cn are related to the original function f. And we'll do this by sort of choosing x carefully and then using some calculus. So first off, we'll make the observation that if we're thinking about choosing x carefully, x equals a looks like a nice number. And then we'll recall that when we expand this infinite series term-wise, we get an expression that looks like c0 plus c1 times x minus a plus c2 times x minus a squared, and so on. So here is our first explanation, our first exploration. Let's go ahead and examine f and set x equal to a. So we see that substituting x equals a on both sides of this power series expansion makes things pretty simple on the right-hand side. A bunch of stuff goes to 0, and we end up with f of a has to be c0. Okay, so let's go ahead and take a derivative and try this again. And our intuition here is that we should be able to differentiate our power series without changing the radius of convergence so long as we are on that radius of convergence. So here's the derivative of the power series. The derivative of the power series looks like c1 plus 2c2 times x minus a plus 3c3 times x minus a squared, and so on and so forth. And you can imagine here, if we plug in x equals a again, we get a bunch of stuff that again goes to 0 at x equals a, so that f prime of a rather, has to be c1. Okay, so you can imagine taking another derivative, and if you take another derivative, you end up with the following expression. So here again, I'm just using the chain rule, taking the derivative, and you can see again, this suggests that we plug in x equals a to the second derivative also. So if we plug in x equals a to the second derivative, here's what we get. We get a bunch of stuff going to 0 again, and f double prime at a has to be 2 c2. And you can continue doing this over and over again, and a pattern comes out pretty quickly. You can see that f triple prime has to be 3 times 2 times c3, and f fourth derivative has to be 4 times 3 times 2 times c4. And we see that every time we take a derivative, we get another integer, and that sure looks like a factorial expansion. So that whatever happens at a, it better be that the nth derivative at a has to be n factorial times c sub n. Now in practice, what we do actually is have the function f be given and solve for the coefficients. So here are those so-called coefficients. It's pretty quickly to solve this equation for Cn. These so-called Taylor coefficients, c sub n is the nth derivative of f evaluated at a divided by n factorial. So let's go ahead and summarize this power series. If f has a power series representation at x equals a, then the coefficients are given by the nth derivative evaluated at a divided by n factorial. So in practice, a problem will say something like find a Taylor series representation or find a power series representation for a given function at a given value a. So here's what you do. You start with the function and a bunch of its derivatives, f prime, f double prime, f triple prime, and so on and so forth, and then go ahead and plug in x equals a and compute f of a, f prime of a, f double prime of a, and so on and so forth, and we'll plug these into our series expansion. As I mentioned, in general, this is called a Taylor series. The Taylor series of f centered at a is given by the sum from n equals 0 to infinity f, the nth derivative at a, divided by n factorial times x minus a to the n power. Now, one special choice that comes up a lot is choosing a to be 0. So the Taylor series at 0 is actually called a Maclaurin series. The Maclaurin series, again, is just a Taylor expansion of f at 0. Okay, so if the instruction says get the Maclaurin series, the Maclaurin series is just the Taylor series of f evaluated at 0. Okay, so here's an example of a Taylor series and looking at convergence. So we'll start with having a look at the Maclaurin series for f of x equals e to the x. Okay, so again, we'll do this by writing down the function f and a bunch of its derivatives, and then evaluating that function f at the desired point, which again, because this is a Maclaurin series, that desired point is at 0. So in this case, it doesn't take too long before we see the pattern. The function is e to the x, its derivative is e to the x, its second derivative is e to the x, and that pattern continues. And plugging in 0, we see there's sort of a similar pattern that makes things pretty easy. Namely that the derivative at 0 is 1, and the second derivative at 0 is 1, and all of those derivatives at 0 are equal to 1. So that tells us what our coefficients are. Remember, our coefficients are just the nth derivative evaluated at 0 divided by n factorial. So here we see the Maclaurin series. E to the x is 1 over n factorial times x to the n power as n ranges from 0 to infinity. So this is a perfectly good power series. We can find the radius of convergence using the ratio test. So I'll leave that ratio test to you. We've actually done this one before, previous video. Have a look at the limit as n goes to infinity of the absolute value of a sub n over a sub n plus 1 over a sub n. You end up with the limit as n goes to infinity of the absolute value of x divided by n plus 1, which is 0 for all x. So we say that the radius of convergence here is infinity. It converges for all values of x. Okay, so to see this convergence from a different point of view, let's go ahead and think about convergence in terms of partial sums of a series. Now, one thing you can do is think about going out to the capital nth term here. And if you stop at the capital nth term, you end up with, as it turns out, exactly a polynomial. So you can imagine the second order polynomial would be something like 1 plus x plus 1 over 2 factorial x squared. The third order polynomial, 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. And in theory, you could do this out to the nth order polynomial also. So here we'll think about the remainder term, the so-called remainder term r sub n of x. We'll define r sub n of x such that f of x is Tn of x plus Rn of x. Or in other words, Rn is f minus T sub n. And then we'll go ahead and say that, that f is equal to its Taylor polynomial, or its Taylor series, excuse me, as long as Rn goes to 0. Okay, so if the remainder term approaches 0, then we say that, that f is equal to its Taylor series. So that's defined more clearly here. We say that the Taylor series converges if f minus t sub n goes to 0 as n goes to infinity. So this gives us a way to check convergence of the Taylor polynomial to the actual function as the number of terms in the Taylor polynomial goes to infinity. Okay, so let's go ahead and have a look at Taylor's inequality. It's a convenient way to bound that nth remainder term. It says that if the n plus first derivative is less than or equal to some constant, then the remainder is less than or equal to that constant m divided by n plus 1 factorial times x minus a to the n power. And our strategy here is that we'll go ahead and use this Taylor inequality to identify convergence of a function to its Taylor series. So here's an example we haven't looked at before, the series representation for the sine function, and we'll show that that series represents f for all x. So the first thing that we have to do is come up with expressions for the function f and its derivatives at 0, Maclaurin series being at 0. So here are expressions for the function and its first 4 derivatives, and as you can see with the 4th derivative we get back the original function again, so there's no need to go beyond that. Now go ahead and plug in 0 and you'll see that we get a lot of terms that simplify pretty nicely. So the function at 0 is 0, the derivative at 0 is 1, the second derivative at 0 is 0, the third derivative at 0 is 1, the fourth derivative at 0 is 0, and you can see that that pattern repeats. So here's the Maclaurin series for sine of x. So here are the first 5 terms, I guess, out to degree 4, and you can see that a lot of those are 0, and I'll go ahead and write a few more terms just so we can see the pattern here. So it turns out that there's a pretty quick way to express this in terms of powers of x and in terms of a sign flip-flopping term. So we'll go ahead and write this as a power series expansion. So here's a power series expansion. Sine of x is the sign flopping term minus 1 to the n times the odd powers of x, which as n goes from 0 to infinity, you get by looking at x to the 2n plus 1, and then we'll go ahead and just divide by 2n plus 1 factorial. So to see that the series converges for all values of x, we'll go ahead and have a look at the n plus first derivative and use Taylor's inequality. N plus first derivative, of course, is either sine x or cosine of x. So in absolute value, that n plus first derivative is always less than or equal to 1. And it's this inequality that we need, really, for Taylor's inequality. Taylor's inequality gives that the remainder term, the nth remainder term, is less than or equal to that value of m times x to the n plus 1 divided by the n plus 1 factorial. So we can see then that r sub n definitely goes to 0 as n goes to infinity because the factorial term forces it to 0. So here again is that inequality. T sub n of x is f of x because the remainder term goes to 0 as n goes to infinity. Okay, I didn't make a slide for this, but I'll go ahead and point out that we can use that series for sine to find a series for cosine. And to do that, we'll just go ahead and differentiate term-wise. So again, here's the series representation for sine, x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th, and so on. Of course, the derivative of sine is cosine, so just differentiate term-wise, and the series expression for cosine is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th, and so on and so forth. Of course, the radius of convergence of both these series is r equals infinity. So a brief summary of some series we know. Again, these are series expansions, Maclaurin series, Taylor series expansions at x equals 0. So we've derived series expansions for the geometric series, for the exponential function, for sine of x, and for cosine of x. And sort of our general strategy is like it was before. We can use these series, manipulating them, integrating and differentiating them to come up with new expressions. So here's a perfectly good example. Let's go ahead and find a series approximation for the integral from 0 to 1 of e to the minus x squared dx. Now, if you recall, this function e to the minus x squared is an example of a function that has no elementary antiderivative. So our strategy here is going to be first to find a series expression for e to the minus x squared, and then integrate that series expression term-wise from 0 to 1. And again, we'll start with the series expression for e to the x. So here's that series expression for e to the x, 1 plus x plus 1 over 2 factorial x squared, and so on. Find a series expression for e to the negative x squared. Just replace x by negative x squared. So here's that series expression for e to the minus x squared. Again, I've replaced x by negative x squared, simplifying and simplifying the powers and negative signs where I need to. Now this expression we can just integrate term-wise from 0 to 1. So here's that expression integrated from 0 to 1. You can see we've got some odd numbers in the denominator from our power rule for integrals, and then we've got some factorials in the denominator from our original series. So just evaluate that at 1 and at 0. Of course, when you plug in 1, you just get the fractions, and when you plug in 0, you just get 0. So here is that series expression. So this is a perfectly good way to represent the definite integral. I'll go ahead and write it as an infinite series using the sum from 0 to infinity. So here's that sum, n equals 0 to infinity. Minus 1 to the n power takes care of the sign flopping term. There are odd numbers in the denominator, so 2n plus 1, and there are also factorials in the denominator, n factorial. Okay, thanks for your attention. I hope you've enjoyed this video on Taylor and Maclaurin series. We'll see you next time.